So we left off last time in deriving those nice kinematics equations. The stipulation on all of those was that the velocity, or not the velocity, excuse me, that the acceleration was a constant value. And I said before we go on and practice those, I want to look at a specific class of problems that do happen quite a bit where the acceleration isn't constant. And what do we do with those? Well, then we're forced to go back and to look at using the equations that velocity is equal to ds dt, that acceleration is equal to dv dt, and maybe even using vdv is equal to ads. So to do that, we'll look at a couple problems here. I'd like to start this problem. Let's say we've got an engine test problem. Maybe we put a jet engine or something into an aircraft, into an airframe, and we're doing some tests on it. And we've got this curve here for acceleration versus time. So the first thing we notice on this thing is that acceleration is not constant. It's not some fixed value. So we know we can't use those nice kinematics equations that we derived that you're probably fairly used to from physics, because acceleration is not constant. And what we'd like to do with this is we'd like to find the velocity and the distance at takeoff, which would probably be important. Figure out how fast we have to be going at takeoff, figure out how far down the runway we're going to travel at takeoff. Those are all probably important things. So let's see if we can do that. We know, of course, that the velocity is equal to ds dt, and we're also going to use the fact that acceleration is equal to dv dt. Is that right? Okay. So what I'd like to do then is talk about rearranging this equation here and say that dv is equal to a dt, and if I integrate both of those sides, I'll come up with essentially the change in v, or the velocity, is equal to the integral of a dt, which is essentially the area under a curve, right? If we've got the acceleration a as a function of t. So let's see if we can make this work out for our purposes. We probably want to go back and look at this curve a little more. We have this linear section here. If we use the simple equation y is equal to mx plus b, we know that this has a slope of the rise, which is going to be 5 divided by the run is 6 times t plus 0, because we have the 0 y-intercept. Then this one is fairly straightforward. This is the simple equation. It's just equal to 5, right? Some constant value in there. So if I put those into this equation here, I can say that the velocity v is going to be equal to the integral of 5, 6 t dt, plus breaking the integral up over those two pieces, one from 0 to 6, so I'll put those limits in here, 0 to 6, and the other one from 6 to 12, so I have the integral from 6 to 12 of 5 dt. You're comfortable with that? So if we go through that then, moving up to the top part of the page here, I could say that the velocity is going to be equal to 5/12 t squared evaluated at 0 and 6 plus 5t evaluated at 6 and 12. And these are probably worth noting. I'm going to come back to these pieces and talk about those, maybe even graph those, get a little better handle on those as we go on and try and talk about position. But for now, we'll continue on and say then the velocity is equal to, if I put the upper limit in here, I get 15 plus 60 minus 30. Of course, the lower limit on that first piece is equal to 0. So when you go through the math there, you come up with, 45 meters per second, about 120 miles an hour somewhere in there. So that seems fairly reasonable. If we came up with something way higher than that or way lower than that, we might be concerned. But I think that's probably okay. Now, before we go on and we look at the displacement, or the distance at takeoff, it might be worth drawing a curve of this thing and looking at those equations that we had up there for the velocity. So we'll talk about time here in seconds. We'll talk about velocity here in meters per second. And if I were to plot these two things, I'd have something that would look like this. Okay, that's the equation 5/12 t squared. And then I have this equation coming up here. That's the equation 5t. Now I have to be careful of that, because if I look at this point here, this is what, 6 seconds? So if I look at 5/12 of 6 squared, that turns out to be equal to what, 15? I think so. And if then I evaluate this equation here, 5 times 6, that's equal to 30. That's problematic, isn't it? Not too happy with that. Those have to be the same point, don't they? So what can I do? I recognize that this one needs to be fixed, and I'm going to have to modify it and say that this one is really what? 5t minus 15? Yeah, would be that constant in there. So now with those equations, I can come back to our expression that v is equal to ds dt, or that s is equal to the integral of v dt, and work this thing out. So I've got s is equal to the integral from 0 to 6 of, what do we have, 5/12 t squared, plus then the integral from 6 to 12 of, what was our new expression, 5t minus 15. These should both be dt. So when we go through this, what do we come out with? We're going to have 5/36 t cubed evaluated at 0 and 6. And then we're going to add to that 5/2 t squared minus 15t. And those are both going to be evaluated at 6 and 12. And when you get done with all of the math there, you're going to come up with 210 meters. Which seems reasonable. Fairly short distance, although not unreasonable. And if it was 21 meters, I'd have real concerns on this thing. But probably okay with that. Questions going through that? One thing that I would take away from this is that when you start to do this, it is probably worth going through the graph on this thing to make sure that you've got those expressions right and there's not a discontinuity in your graph. Any questions? Well, that one was fairly straightforward. We'll move on to one that's maybe a bit more difficult, or I should say maybe not as obvious. And let's try this problem here. Let's say that we are given a velocity position curve. So instead of having an acceleration, I mean the previous problem, we had acceleration time, and it should not surprise us that we integrated to get velocity time. Okay. Well, this is a little bit of a different twist. I've got velocity position. So the horizontal, one of the coordinates, it is not time. I have velocity versus position. A lot of times this comes up, so we want to be able to deal with this. When we get done with this, the question will probably come up, how did you know to do this? The answer is going to be, just take practice. It just takes practice. So let's see if we can get through this. We've got velocity as a function of displacement. So as displacement goes from 0 to 500 feet, our velocity is going from 10 to 60 feet per second in a linear fashion. Okay. And what we'd like to find is we'd like to build a acceleration displacement plot. So see what acceleration looks like in this kind of an environment. Presumably it's not going to be constant. I guess if we find out that it is constant, I don't think it will be constant, but if it is constant, we could have used those easier equations, but it probably won't be, so it's probably smart not to use them. And we'd also like to find the distance, or the time to travel that 500 feet. So let's get started with this. If I look at the equation of this thing, what do I have? The rise over the run, so it's going to go from 10 to 60, so I have a rise of 50 over a run of 500. That would then be s, because that's our horizontal variable, plus our y-intercept, which is 10, right? So I could say that the velocity as a function of s is really equal to, what, 0.1 times s plus 10. So that's just coming off the equation y is equal to mx plus b, parameterizing that. So let me start with that expression. I'll come down here and I'll work on this and say that then v is equal to 0.1 s plus 10. And I'm going to differentiate that. I'm going to say that dv is equal to 0.1 s plus 0. Of course, when I differentiate it, the 10 goes away. And I now have dv, right? So if I go back and I look at our friend a ds is equal to v dv, I can put dv in there. So I've got a, and then ds. Let's see, do I have a value for ds? Yeah, from here I could solve for, this would be, I'm sorry, this is not s, but this is rather ds, isn't it? Okay. So if I solve this for ds, that's going to be equal to 10 dv, is that right? Yeah, now we're okay. So now I have an expression for ds, and I can say that this is equal to 10 times dv is equal to v dv. We okay with that now? Okay. So I've got a is equal to ds, which I've substituted in my 10 dv, is equal to then v dv. So I've got a dv on both sides. I can cancel that and come up with essentially a reduction that v is equal to 10 times a. And do I have an expression for v? Yeah, that's what I started out with up here. That was our expression for v, wasn't it? So I could come up here then and say that 10a that we just got down here is equal to v, which we also know is equal to 0.1 times s plus 10. So if I solve for a, I can divide that again by 10, and a is equal to 0.01 s plus 1, dividing by 10. So that is a as a function of s, isn't it? That's what I'm looking for with the plot. So I should be able to plot that thing. So let me make this plot then. So there's s in feet and a in feet per second squared. And what's that going to look like? If I put 0 in there, what do we come up with? 1. And if I put 500 in there, what do we come up with? 6. And what kind of an expression is it between those? Looks like a linear expression, right? So there's our plot of acceleration versus position. So was it smart that we didn't go with those kinematics equations that we developed last time? Yeah, because it's not constant acceleration, is it? The acceleration varies. I don't know really how it varies with time, but it varies linearly with position. So it certainly is not constant acceleration. Okay, so the second part of it, we've got this plot done. You okay with the plot? We'd like to then look at the time to travel 500 feet. So the time to travel 500 feet. why don't I say that my velocity, which I know is equal to what, ds dt, is that right? That was equal to 0.1 s plus 10. You buy that? So I could rearrange this a little bit. I could cross multiply and say that I have ds divided by 0.1 s plus 10 is equal to dt. And then if I integrate both sides of this, that should give me time, shouldn't it? Okay. So I'm going to integrate this from 0 to s, which would be s equals 500. And this is going to go from 0 to t. So I can come up then with t is equal to, that's the left hand or right hand side, that's fairly easy, right? Left hand side, how do I integrate that? Looks like the natural log, doesn't it? Yeah, I think I'm going to have 10 times the log of 0.1 s plus 10, and I have to then evaluate that at 0 and 500. I mean, you could put that into a computer algebra system or something, but I think most of you are close enough to your math. You remember that that was turned out to be a logarithm. Then you go through this, you come up with 10 times the natural log of 60 minus 10 times the natural log of 10, which when the dust all settles from the math, time is equal to 17.9 seconds. Which again seems fairly reasonable. Did I get off on this? Questions with that? Yeah. Wondering about the what? The 10 in front of the natural log? Well, that comes from this 10 down here. Yeah. So if that was a 1, we wouldn't have it. So you could test this and you could differentiate this and see if you get back to that. Other questions? Any questions? So sometimes the question comes up, I mean, how would you know to do this and how would you know to do that substitution? That just a matter of practice. Okay. The last problem was probably a lot easier. We just continued to do integration. There was no real question which way we were going to go. This problem is a little more difficult in which substitution you make and things like that. And all I can say is just takes practice. You got a few homework problems that will test you on this. Other questions? So with those problems at hand, I'd like to go back and look at problems where we have constant acceleration. So maybe I don't know that we call this a projectile problem, but it really is a projectile problem where we have acceleration equaling the acceleration of gravity. So we have some cliff or something, and we have a car running off the edge of a cliff, or we have a ball being thrown horizontally off the edge of a cliff or a building or something like that. And we can, well, the velocity that this is coming off of here with, the velocity that the car might be having, or the person running off the cliff, or the ball being thrown off of the cliff, that might not be well known, but we can fairly easily figure out the height of this, the height of the cliff, the height of the building, and we can figure out the distance that it comes off or is thrown off, where it hits. Okay, we can measure those pretty easily. So what I'd like to do with this scenario is I'd like to, one, find the time that this is going to be in the air. How long is this object going to be in the air from this point up here to its impact down there? I'd like to find the original velocity v0, this horizontal velocity v0, and I'd also like to find the impact velocity here when it hits the ground. And I'm going to hopefully find those all as a function of x and y, because x and y are pretty easy to measure. There's always a classic example of a physics test where a student is asked to describe how you use a barometer to determine the height of a building. And probably the instructor is hoping that the student would talk about measuring the barometric pressure at the base and then go up to the top, measure the barometric pressure. And we'd expect the barometric pressure to be less at the top, right? We could figure out how tall the building was based on that. But you could take that barometer and use it a little differently, right? You go up to the top of the building, throw the barometer off, and also figure out the height of the building. If you just dropped it off, it'd be a little easier. It's just a free fall problem. But if you knew how to throw it at a certain velocity, maybe you had a friend that was a pitcher that could, muster up 90 miles an hour throwing a barometer, you could have them wing it off the building and see how far it goes. So a kind of an interesting problem here. And the nice thing is in the vertical direction, our acceleration is constant as g. And we're going to take that the acceleration in this direction is equal to 0. That means that we're going to neglect air drag. Yes? Well, I'm taking it positive down. Okay. Yeah, it is going down, so we need to be clear on that. In the horizontal direction, I'm going to take acceleration equal to 0. That means I'm neglecting air drag. So if we're throwing a small barometer off or a steel shot or something like that, it's probably not a huge problem. If we're throwing a feather off, then that's going to be a real problem for us. So things that have a large aerodynamic surface, this may not be a good assumption. But for certain things, it's probably a decent assumption. It makes our problem a lot easier. So let's see if we can get started with this. Back in my notes here a little bit. So if I were to look at the, I'm going to use the equation, start out with the equation that S, the position, is equal to the original position, S naught, plus V naught T, plus 1/2 AT squared. So I'll start with that equation there. And if I look in the y direction, so maybe I'll say that this is the y direction. Taking y as up, y is the vertical direction. What's the initial velocity of this thing? I mean, the initial position, if we reference our initial position here, I could say that this is equal to 0, right? And then the initial velocity, this person is throwing it horizontally, right? So this would be 0, wouldn't it? Our vertical velocity is 0. Vertical velocity is equal to 0. The person is throwing it off horizontally. So I can say then that S, which we'll say is equal to y, y then is equal to 1/2 times the acceleration, which I will call g, t squared. So I can solve for t if I want to from this thing, that t is going to be equal to the square root of 2 times y divided by g. Okay. So we can come up with an expression here for the time, really just looking at free fall or looking at the vertical direction. Now if I wanted to look at the units on this, let's say, convince myself hopefully that this answer is correct. If I look at English units, what would I have? I'm going to have 2 isn't going to have any units, but y would have units of feet or inches, and then g would have corresponding units of feet per second squared. So I'm going to come up with the denominator of a denominator as a numerator. The feet cancel. This is then the square root of second squared, which would be seconds, wouldn't it? Seems reasonable for time. So I think we have a good equation here for time. We can say that's the time of free fall. Questions with that? Okay, so we got time. Let's see, V naught. What's V naught going to be? Well, once I have time, I can go back to the really fancy equation that distance is equal to rate times time. That's the one I said you use every day. Okay, we could clutter it up with all kinds of symbols and whatnot, but distance equals rate times time. So in a horizontal sense, and we agreed that vertical velocity and horizontal velocity were independent. So I can look at this horizontal velocity. The distance is going to be x that this travels in the horizontal direction, isn't it? And what rate is that going to be? I mean, the stipulation on this equation was that acceleration has to be equal to 0. That's what we had there, isn't it? 0 air drag in this thing. So my rate is really just v naught, isn't it? Times the time t. So I could say that v naught then is equal to x, the distance that's covered, divided by t. You can see that the units work out on that, and if you want to, you could then substitute the t in here. I mean, you can make that substitution for t if you want to. I won't belabor that point. But the original velocity is fairly easy to get at if we know how far this thing travels, assuming that there's no air drag. Or maybe we should say assuming negligible air drag. Now the last part of this problem is to look at impact velocity, and maybe we should talk a little bit about what happens at impact. So it comes down here, and I'm going to kind of draw an exploded view of what's going on right there. It's going to hit the ground, and it's going to have a couple of velocities. It's going to have one velocity like this, which will be the velocity in the y direction, right? And it's going to also have a velocity like this, the velocity in the x direction. And those would be resolved vectorially to look something like this. You would expect that to land and kind of make a divot in the ground that's going in that direction, right? If you studied how a golf ball makes a divot, or you know, throwing a shot or something like that, that probably should not surprise you. So this is what we're looking for, the impact velocity, the resolution of Vx and Vy. So let's see if we can do that. What is Vx? That's just V naught, because with no acceleration, that's unchanged, isn't it? It's the horizontal velocity at the top of the cliff. It's the horizontal velocity down there at impact. What's Vy going to be? Well, I could say that Vy is equal to V naught y plus AT, right? I mean, didn't we have that V is equal to V naught plus AT? Wasn't that one of our equations from last time? So I could take that then and give it the subscripts that match our problem. So Vy is equal to V naught y plus AT. So what's the initial velocity in the y direction? I mean, we have V naught, that's in the x direction, but the initial velocity here in the y direction, V naught in the y direction, is equal to 0, isn't it? Okay, so that's equal to 0. So I can say then that Vy is just equal to AT. So when I put these in and I resolve these, I can say that the impact velocity, or the magnitude of the impact velocity, is going to be equal to the square root of V naught squared. Keep these separate here. V naught squared plus Vy squared. And what did we make our substitution there? This was V naught squared plus, what did we say Vy was? AT. Okay. Now if I multiply the acceleration times the time, do I come up with velocity units? Yeah, I actually do, don't I? Okay. Questions with that? So there's some results here. You could come back and put in whatever numbers that you wanted to. But the time is probably worth remembering. That will come up over and over again because that's the same time for free fall. The distance covered is important. Another classic example of this is dropping a package from an airplane, right? You can't wait till you're just directly over the target because you're going to end up dropping it past the target. So you've got some homework problems that talk about that too. Questions of that? Well, let's move on then. So I would say that last problem was projectile motion, but a lot of times if you were to look up projectile motion in the textbook or a physics book or something like that, they're going to give a more classic problem here where we have some projectile, whether this is the trajectory of a golf ball or a baseball or a water balloon or maybe a cannon or something like this. We're going to fire it at some angle. We're going to say that angle is phi, and then we're going to expect it to come up to some maximum height, h, and then start to fall back to Earth and strike the ground there. We'll assume that this is horizontal here, that this is level, and strike the ground where at the same vertical elevation that it started, someplace downrange. So I'd like to go through a few things here. I would like to come up with what r is equal to. I'd like to come up with what h is equal to, the height. Certainly would like to come up with the time from A to C, the hang time on this thing. And then maybe once we've got those expressions, we talk about maximizing the range. Certainly if we're doing cannons or something, that probably becomes very important, trying to maximize that. So let's see how that works out. To do this, I'm going to look first in the vertical direction. So looking at in the vertical direction, I could break this velocity if I say that I have, and I'm really just coming in and blowing up what I have over there, and saying that this V naught at some angle phi could be broken up into V naught cosine phi and V naught sine phi. You okay with that? So in the vertical direction, I'm going to have V naught sine phi. So I'm going to start, we're going to say that G is constant. So we get to use our nice kinematics equations for this. And I think last time we derived the expression that, V2 squared was equal to V1 squared plus 2A delta S. You may see that written a little differently. I think I'm going to write it a little differently and say that this is V squared is equal to V naught squared plus 2A S. Just kind of changing the subscripts a little bit. Well, if I solve for S, I can say that S is equal to V squared minus V naught squared divided by 2 times the acceleration A. So I'm going to make my substitutions for this. So what is, in the vertical direction, what's S? If I'm going from A to B, what's S? I guess I need B. There's B. Well, S is equal to H, right? We're going to, in the vertical direction, we're going to travel from there up, and we're going to cover distance H. So we have H is equal to, what's my final velocity going to be? I mean, to do this, we have a little bit, how would you find where the apex was? Yeah, the velocity is 0. I mean, one way of finding the apex, well, that's the highest that it goes. But another way of finding it is it goes up, it goes up, it goes up, it stops momentarily, and then it starts to fall back down, right? Okay. Because we talked about the bullet dropping. That was our experiment on the Great Salt Flats last time. You could also, if someone were to throw this thing up with the velocity here, V naught sine phi, it would go up, and then it would come down, right? And actually over the same amount of time. So our velocity here, that's our second velocity, so that's equal to 0. It's initially at rest right at the time. It comes to rest up there. It goes up, rests momentarily, and then starts to fall back down. And then I'm going to have to subtract off the original velocity. What was our original velocity? V naught sine phi. Thank you very much. And I have to square that. So I'll square this. I'll square that. And then I'm going to divide this thing by 2 times the acceleration, which the acceleration is what? Yeah, and I'm going to be a little more careful here. I'm taking positive up, so this is positive y. So if g is going down, I'm going to say that it's minus g. Okay. So I could say with this, when it gets all cleaned up, that h, the height of this thing, is equal to v naught squared sine squared phi divided by 2g. Do the units work on that? Let's do a quick units analysis here. We're going to say, let's see, velocity. Why don't we say feet squared per second squared, because that'd be velocity squared. There should be no units on sine squared phi, right? Then I'm going to divide no units on 2, but g is going to be feet per second squared. Everything cancels out except for a foot, doesn't it? Is that what we'd say the height was? Yeah. You watch someone do a interesting punt or something in football. Yeah, it went way up there. It must have been 100 feet high, right? We measure the distance in feet. So I think we've got h down. I think maybe I'll tackle time. So let me come up here and talk about s is equal to s naught plus v naught t plus 1/2 at squared. That's an equation we saw last time, wasn't it? Yeah. I'm going to say that s naught is equal to 0. I'm going to say that I started a 0 point. So I'm going to rearrange this a little bit, and I'm going to say that 0 is equal to v naught t plus 1/2 at squared minus s. Maybe I'll rearrange that a little more. I'll say that I have 0 is equal to multiplying both sides by 2, I would get at squared plus 2 v naught t minus 2s. You okay with that? I'm just setting up a polynomial there. You know what's coming next. We're going to use the quadratic equation and solve this for t. So we could say that the time was equal to minus b, so that would be a minus 2 times v naught plus or minus the square root of 2 squared, which is 4 v naught squared. And then I'm going to have minus ab, so this will end up being positive 4a times 2s. And then I have to divide this entire thing by 2a. What's that? Oh, in here? But isn't it plus or yeah, I got rid of it there with the front side. I'm going to go ahead and take, because I've done this before, I don't want to belabor this, I'm going to take the positive root. So take the positive root. So that means that t is going to be equal to minus 2 v naught plus 2 times the square root v naught squared plus 2as divided by 2a. And I also factored a 4 out of that radical as a 2. You okay with that? When I say take the positive root, I just took the positive sign up there. If you did the negative, you get some weird answers that you wouldn't recognize. So, good with that so far? Yep. Yeah, I'm not done yet, but you're absolutely right. I can cancel out the 2's. So I've got time t is going to be equal to, I'll rearrange it a little more. I mean, obviously cancel out these 2's. And rearranging this a little more, I have the square root of v naught squared plus 2as minus v naught all over a. Okay. And I could, maybe I'll put a box around this. I could say in, this is actually all in general. Okay. So in general, we could say that. Now I'd like to take that general notion and apply it to our going from A to B. So let me go on to the next page here. And I'll rewrite this thing. Okay, so that's my general expression, and I would like to apply this t from A to B. And to refresh you, if we look at the trajectory path on this thing, we had A here, we had B at the top, and we had C then at impact. So I'm looking just at going from launch up to the apex, up to the top there. So what's our V naught going to be on this thing? We're going to have to, everywhere that we see a V naught in there, we're going to have to substitute in V naught times the sine of phi, because I just want to look in the vertical direction. And what's A going to be? Everywhere I see A, I'm really going to have to put in a minus G, right? And when I see S, what's S going to be? H, which we said H was equal to what? V naught squared sine squared phi divided by 2g, right? Okay. So if I make those substitutions, if I substitute these back into here, I'm going to come up with something that looks like this for time. This is time from A to B. It's going to be the square root. This is going to get ugly before we're done. Let's see. V naught squared sine squared phi. So I square those. Plus 2 times minus g times s, which is v naught squared sine squared phi, all divided by 2g. There's our radical, and we're dividing then the radical by what? A, which is minus g. So if I look in the radical, I get to cancel this with everything here except for the negative sign, right? Oh yeah, thank you. So minus v naught, which is what? V naught sine phi. Good. Okay. Thank you. I almost forgot that. Because that would have been bad, because what's under the radical? When I cancel this 2g in the denominator here with that 2 and that g, noting the negative sign, I now have v naught squared sine squared phi minus v naught squared sine squared phi. So the radical is what? 0, isn't it? Yeah, everything in the radical is equal to 0. And I can say then that time from A to B is equal to v naught sine phi divided by g, canceling the negative in the numerator and the denominator. So I'm glad she corrected us, because we would have been trying to say that that was 0, which wouldn't have made sense. Okay. So V naught sine phi over G. So now, if I look at the time from B to C, what's that going to be? It's going to end up being the same thing, but to derive that, we could really think of it as free fall. What was our free fall expression from earlier in the day? We said it's equal to 2y over g. Is that this one here? Yeah. So the square root of 2y divided by g. So in our case, what do we have? B to C is going to be equal to the square root of 2y. How far is it? That's how far it's falling, right? So that's 2 times h divided by g, which would be equal to the square root of, what do we have for h? V naught squared sine squared phi divided by 2g, and then I had this 2 in there that I better put in. That was that 2 right there. And then I have another g, so I'm going to end up with this being squared, right? I have the g from h, I have the other g there. So I get to cancel the 2's, and everything is squared, so this turns out to be equal to what? V naught sine phi divided by g. So those of you that said it was the same from A to B as B to C, you're correct. Now if we were to look at either one of these in terms of units, what's a units argument going to look like on this? Maybe feet per second. Sine phi doesn't have any units, then G is going to be feet per second squared. So that turns out as seconds, right? So we can say, to finish up here, that the time from A to C is really just the sum of these. That is the time from A to B plus the time from B to C, which gives me 2 times V naught times sine phi divided by G. So we've got a little ways to go on this problem. We've talked about the height. We've talked about the time. We've still got to look at the range, and then we've got to look at maximizing the range. And then we've got to have some fun with it. Well, thank you for watching, and take care until next time.